Hello, and welcome to Space for Sleep. The question of whether we are alone is not one question. It is several questions nested inside one another. Is there life anywhere beyond Earth? Even microbial life? Even something simple? Even something hidden under ice or buried in ancient rock? Did life begin more than once in our own solar system? Are there living oceans inside the moons of Jupiter and Saturn? Do any nearby exoplanets carry atmospheric signs of biology? Has intelligence evolved elsewhere? Has technology evolved elsewhere? And if technological civilizations exist, why have we not seen or heard anything that unmistakably belongs to them? For most of human history, these questions belong to philosophy, religion, speculation, and imagination. People could look up at the night sky and wonder whether the stars were other suns, whether those suns had worlds, and whether those worlds had living things. But there was no way to test the idea. The question was too large, too distant, too far beyond the instruments available. That has changed. Not completely, but genuinely. Modern astrobiology is no longer only a thought experiment. It is a scientific program built from biology, chemistry, planetary geology, telescope spectroscopy, spacecraft exploration, radio astronomy, and the study of extreme environments on Earth. We have learned that the ingredients of life are not rare curiosities. Organic molecules exist in interstellar clouds, in meteorites, in comets, in the atmospheres of moons and planets, and in the disks around young stars. We have learned that liquid water, or evidence of past liquid water, is common in the solar system. Mars was once wetter. Europa almost certainly has a global ocean under its ice. Enceladus actively sprays material from a subsurface ocean into space. Titan is rich in organic chemistry. Exoplanets are not rare. They are everywhere. And yet we have not found life anywhere else. Not a living cell. Not a fossil that is beyond dispute. Not a confirmed biosignature gas. Not a radio signal proven to come from another civilization. Not a technosignature. Not one unambiguous second example of biology. That is the tension at the center of the search for life. The universe looks chemically fertile, planets look abundant, habitable environments may be common, and still the only life we know is here. This episode is about that tension. It is about what life is, how difficult it may be to start, where we are looking, what counts as evidence, why false positives matter, what SETI has and has not ruled out, and what the silence of the universe might mean. The chemistry of space itself is one of the reasons the search for life became scientifically plausible. Interstellar space is not chemically empty. It is thin, cold, irradiated, and harsh, but it contains molecules. Radio telescopes have identified carbon monoxide, water, ammonia, methanol, formaldehyde, hydrogen cyanide, and many more complex species in molecular clouds. Dust grains in those clouds act as tiny reaction surfaces, allowing atoms and simple molecules to meet, stick, react, and build larger compounds in environments where gas-phase chemistry alone would be too slow. When young stars form, this chemical material becomes part of protoplanetary disks, comets, asteroids, and eventually planets. Meteorites have brought some of that cosmic chemistry to Earth. Carbonaceous chondrites contain amino acids, nucleobase-related compounds, sugars or sugar precursors, and a wide range of organic molecules. These are not organisms, and they are not evidence of life in space. They are evidence that prebiotic chemistry is not confined to one planet. The raw ingredients of biology can form naturally before a planet becomes biological. This matters because it changes the starting conditions. Early Earth did not have to invent every organic molecule from scratch on its surface. Some chemistry happened in the atmosphere, some in oceans, some at vents, some on mineral surfaces, and some may have arrived from asteroids and comets. The same may be true elsewhere. A A young planet in a chemically rich system may inherit part of the inventory needed for life before it ever has stable oceans. But ingredients are not a recipe. Amino acids in a meteorite do not equal life. Organic haze on Titan does not equal life. Methane, carbon dioxide, hydrogen, cyanides, or complex carbon compounds do not equal life. Astrobiology is the science of separating chemical possibility from biological reality. The universe appears rich in prebiotic material. The unknown is how often that material crosses the threshold into self-sustaining evolution. Before looking outward, there is a difficulty that has to be faced directly. We do not have a perfect definition of life. That may sound strange. Life seems obvious when it is a tree, a dog, a bacterium under a microscope, or a human body breathing in a room. But at the boundary between living and non-living systems, the clarity fades. A virus carries genetic information and evolves, but cannot reproduce without hijacking a cell. A flame consumes fuel, maintains a structure, and spreads, but does not store heritable information. A crystal can grow and copy its pattern, but does not metabolize. A computer virus replicates and mutates in an informational environment, but is not chemistry. A sterile mule is alive though it cannot reproduce. A dormant bacterial spore can remain metabolically almost inactive for thousands or perhaps millions of years and still return to activity under the right conditions. So astrobiology uses working definitions rather than one final philosophical definition. A common NASA-style formulation describes life as a self-sustaining chemical system capable of Darwinian evolution. This is not perfect, but it is useful. It focuses on chemistry, energy, replication, and evolution, the features that make life detectable as a physical process rather than as an intuition. This matters because any search for alien life is also a search for unfamiliarity. If we go to Mars and find cells with DNA, proteins, membranes, and a genetic code nearly identical to ours, the interpretation would be one kind of challenge. It might mean life traveled between Earth and Mars. If we find a completely different information molecule, a different biochemistry, or a different chirality, a different handedness of biological molecules, the interpretation would be far more dramatic: a second origin. A second origin would be one of the most important discoveries in science. It would show that life is not a one-time accident unique to Earth, but a process nature can repeat. Even if that second life were only microbial, even if it were hidden in an ocean under ice, it would change the meaning of biology. Biology would no longer be the study of one planetary lineage. It would become a comparative cosmic science. This is why astrobiologists care not only about finding something alive, but about understanding whether it is independently alive. A microbe on Mars that shares Earth's biochemistry might be astonishing, but it might also be a cousin. A microbe on Europa or Enceladus with a different biochemical architecture would be something even larger. Evidence that life can arise separately wherever chemistry and energy allow. Earth is both our best guide and our greatest bias. Every organism we have ever studied descends from a common ancestor. Bacteria, archaea, animals, fungi, plants, algae, and every microbe in every extreme environment are variations on one planetary lineage. They use DNA or RNA, ribosomes, proteins built from amino acids, lipid membranes, ATP-based energy currency, and a genetic code that is broadly shared across life. This unity is beautiful, but it is also limiting. We do not know which features are universal requirements of life and which are historical accidents of Earth. For example, all known life uses water. Is water necessary, or merely the solvent that was available here? All known life uses carbon. Is carbon required, or only overwhelmingly favored? All known life uses a narrow set of amino acids. Are those 20 standard amino acids chemically inevitable, or did early evolution settle on them by chance? All known life uses left-handed amino acids and right-handed sugars. Is that handedness a frozen accident from early Earth? Or does life everywhere choose one-handedness over another for deep chemical reasons? These questions matter for detection. If alien life is close to Earth life in chemistry, our instruments can be designed to recognize it. If it is radically different, the risk of missing it grows. A life detection instrument that searches only for DNA would fail on a world where life uses a different information polymer. A biosignature framework built only around oxygen could miss a biosphere based on anaerobic chemistry. A mission searching only for cell shapes could be fooled by minerals or could overlook organisms with unfamiliar structures. This is why astrobiology increasingly distinguishes between life as we know it and life as we do not yet know it. The first is searchable with confidence. The second requires agnostic biosignatures, patterns of complexity, chemical selectivity, disequilibrium, and information that might indicate life without assuming the exact molecules Earth uses. The strength of this topic is that every possible answer is dramatic. If life is common, then Earth is not a miracle but an example. If life is rare, then this planet is more precious than we usually imagine. If microbes are common but intelligence is rare, then biology may be easy and civilization difficult. If intelligence is common but silent, then the galaxy may be full of choices and behaviors we do not yet understand. There is no boring outcome. The search for life is interesting because every answer changes the meaning of home. Life, at its most fundamental level, is chemistry, not magic, not vitality, not some principle outside the physical world, chemistry. A set of chemical reactions that are self-sustaining, self-replicating, and capable of heritable variation. This definition, minimal and almost harsh in its plainness, is the working definition that astrobiology uses, and it is worth dwelling on because it guides everything else. Self-sustaining means the chemistry maintains itself against the thermodynamic tendency toward equilibrium and disorder. Life is a persistent disequilibrium, a set of reactions that continuously replenish their own components by extracting energy from the environment, whether from sunlight, from chemical reactions between geological materials, from the heat of a hydrothermal vent, or from a dozen other energy sources available on Earth and potentially elsewhere. Every living organism is, thermodynamically, a machine for keeping itself far from chemical equilibrium for as long as its energy source allows. Self-replicating means the chemistry copies itself. The information that encodes the specific structure and behavior of an organism is stored in a molecule that can be copied, imperfectly, but faithfully enough that offspring resemble parents. On Earth, this molecule is DNA, which stores biological information in sequences of 4 nucleotide bases, and is copied by a remarkable molecular machinery into RNA and then into proteins, the molecules that do most of the structural and catalytic work of cells. Heritable variation means the copying is imperfect in ways that can change the information transmitted to descendants. Mutations, recombinations, and other changes in the genetic information produce organisms with slightly different properties. When those properties affect the organism's ability to survive and reproduce, when some variants are better at extracting energy or avoiding destruction than others, the variants that reproduce more successfully pass their traits to more offspring, and the population changes over time. This is natural selection, the engine of evolution, and it requires no guidance or direction. It is the automatic consequence of heritable variation in a world where reproduction is limited by resources. With this minimal definition, self-sustaining chemistry capable of heritable variation, life becomes something that the physical universe might produce through processes that don't require any special principle beyond chemistry and physics. Whether the specific chemistry of life on Earth, centered on carbon, using water as a solvent, encoding information in nucleic acids, doing catalysis with proteins, is the only chemistry capable of producing life, or whether other chemistries might work in other environments, is one of the deepest and least resolved questions in astrobiology. The case for carbon-based life is strong, and it rests on carbon's unique chemical properties. Carbon forms stable covalent bonds with itself and with oxygen, hydrogen, nitrogen, sulfur, and phosphorus, the other major elements of biochemistry, in an enormous diversity of configurations. Carbon chemistry can produce molecules of arbitrary complexity, chains, rings, branching structures, three-dimensional frameworks. No other element approaches carbon's ability to form structurally diverse, complex molecules. Silicon, carbon's neighbor in the periodic table and the most commonly cited alternative, can form some of the same types of bonds, but silicon-silicon bonds are weaker and silicon-oxygen bonds, unlike carbon-oxygen bonds, tend to produce solid, insoluble polymers rather than the water-soluble organic chemistry that life on Earth depends on. In principle, silicon-based chemistry might support some form of life in a drastically different environment, hot, dry, with a solvent other than water, but it would need to solve the stability and solubility problems that make silicon far less versatile than carbon for complex chemistry. The case for water as a solvent is similarly strong in the specific context of Earth-like life. Water has an extraordinary set of properties. It is liquid over a wide temperature range. It is a polar molecule that dissolves ionic and polar compounds efficiently. It expands when it freezes, protecting liquid water beneath ice from the cold above, and it supports an enormous range of chemical reactions that are important in biochemistry, including the hydrolysis reactions that break chemical bonds and the condensation reactions that form them. Other solvents, ammonia, methanol, ethane, sulfuric acid, have been proposed as alternatives that might support life in different environments, each with specific advantages and disadvantages. The most serious alternative for astrobiological purposes is ammonia, which is liquid at temperatures of -78 to -33 degrees Celsius at atmospheric pressure, potentially enabling life in cold environments where water would be frozen. But ammonia lacks many of water's specific chemical advantages, and no known life uses it as a primary solvent. The most difficult part of life detection may be deciding how much evidence is enough. For an ordinary scientific claim, uncertainty can be tolerated. A new mineral, a new comet, a new type of exoplanet. These discoveries matter, but they do not instantly change humanity's understanding of itself. A claim of life beyond Earth is different. It would be culturally, philosophically, and scientifically enormous. The standard of evidence has to be higher because the consequences of being wrong would be large. This creates a difficult balance. If scientists are too cautious, they may hesitate to say what the evidence implies. If they are too eager, they may damage public trust by announcing life and later retreating. The responsible path is slower. Describe the evidence precisely, state what is known, state what is not known, and allow the conclusion to strengthen only as alternatives fail. The phrase potential biosignature exists for this reason. It protects the mystery from both dismissal and exaggeration. A life detection mission has to look for more than one kind of evidence, because life is not a single molecule. On Earth, living systems create patterns across many scales. They create molecular patterns, complex organic molecules with specific structures, repeating units, and chemical preferences. They create isotopic patterns. Biology often prefers lighter isotopes because chemical reactions involving lighter atoms proceed slightly faster, leaving measurable fractionation in carbon, sulfur, nitrogen, or iron. They create structural patterns, cells, membranes, colonies, mats, layered deposits, microscopic textures. They create energetic patterns, chemical disequilibria that should not persist unless something is maintaining them. They create ecological patterns, gradients, cycles, and interactions between organisms and environments. A single one of these patterns can be misleading. Abiotic chemistry can produce organics. Minerals can produce cell-like shapes. Non-biological reactions can fractionate isotopes. Geology can create layered structures that resemble microbial mats. But multiple independent patterns pointing in the same direction become much harder to dismiss. This is why astrobiologists often talk about a ladder of life detection rather than a single yes or no test. The lower rungs are habitability, water, energy, elements, stability. The middle rungs are possible biosignatures, organics, mineral textures, disequilibrium, isotopic hints. The upper rungs require convergence, several lines of evidence, in the right environmental context, with abiotic alternatives examined and found insufficient. The most responsible life detection would not be a dramatic claim made from one instrument on one day. It would be a case built from chemistry, geology, context, replication, and independent confirmation. That may sound less exciting than a headline. It is also the only way such a discovery would be trusted. The astrobiology community generally works with a pragmatic approach, search for life as we know it, centered on carbon and water, while remaining open to the theoretical possibility that radically different chemistries could produce life in radically different environments. This is not close-mindedness, but practicality. We know exactly what chemical signatures to look for if we're searching for Earth-like life, while searching for an unknown, unpredictable chemistry is much harder to specify observationally. The uncertainty around the origin of life is not a minor gap in the story. It is one of the central reasons the question of alien life remains unresolved. If life begins easily, the galaxy may be full of microbes. If life begins only after an extremely rare sequence of events, then even a universe full of habitable planets might still be biologically quiet. Earth gives us only one example, and one example is not enough to measure probability. The early Earth was not a gentle laboratory. It was volcanically active, repeatedly struck by impacts, heated internally, chemically reactive, and surrounded by an atmosphere very different from today's. There were oceans, but also hydrothermal systems, tidal pools, mineral surfaces, ultraviolet radiation, lightning, impact chemistry, and cycles of wetting and drying. Each environment offers a different possible pathway for prebiotic chemistry. The famous Miller-Urey experiment in 1953 showed that simple gases, when exposed to electrical sparks under early Earth-like assumptions, could produce amino acids, the building blocks of proteins. That experiment did not solve the origin of life, and the exact atmosphere used in the original setup is no longer considered a perfect model of early Earth. But it demonstrated something important. Organic complexity can emerge from simple chemistry under plausible natural energy sources. Since then, origin of life research has become much more sophisticated. Scientists study how nucleotides could form, how membranes could assemble from fatty acids, how mineral surfaces might concentrate molecules, how cycles of drying and rehydration might promote polymer formation, how hydrothermal vents might generate natural proton gradients, and how networks of reactions might become self-sustaining before anything like a modern cell existed. There are two broad instincts in the field. One begins with information. Find a molecule capable of storing and copying instructions, and evolution can begin. This is the RNA world tradition. The other begins with metabolism. Find a network of reactions that harvests energy and maintains itself, and information may emerge later. This is the metabolism first tradition. There are also hybrid models, where simple compartments, reaction networks, and information polymers co-evolve rather than appearing in a strict order. None of these approaches has yet produced a complete demonstrated pathway from non-living geochemistry to a self-sustaining, evolving cell. That does not mean the problem is impossible. It means the transition was complex enough that we have not yet reconstructed it. For astrobiology, the consequence is profound. We can identify habitable environments more confidently than we can estimate how often life begins in them. The origin of life on Earth is one of the great unsolved problems in biology, and its solution, or lack of it, has direct implications for whether life might have originated elsewhere. We don't know how life originated on Earth. This is worth stating plainly, because popular accounts sometimes imply that the broad outlines are known even if details remain to be worked out. In fact, the transition from chemistry to biology, the specific set of chemical events that produced the first self-replicating, heritable system from non-living chemistry, is not understood, and the field of origin of life research remains one in which genuinely competing theories are vigorously debated without consensus. What we do know is that life appeared on Earth remarkably early. The oldest direct evidence for life, carbon isotope signatures in ancient rocks from Greenland and Canada that indicate biological fractionation of carbon isotopes, and possibly microfossils in Australian cherts, dates to roughly 3.5 to 3.7 billion years ago, and some interpretations of isotopic data push potential biological signatures back to 4 billion years. The Earth itself is 4.5 billion years old, and the period from formation to the first appearance of life was marked by intense meteorite bombardment that likely periodically sterilized the surface, at least to shallow depths. The actual interval between when stable conditions for life existed and when life appeared may have been quite short by geological standards, perhaps tens to hundreds of millions of years. This rapid emergence of life after the formation of stable conditions could be interpreted in two very different ways. It might indicate that the origin of life is easy, that given the right chemistry and the right conditions, life arises quickly and inevitably, making it likely to have arisen on other suitable worlds throughout the galaxy and universe. Or it might indicate a survivorship bias in the observation. If the origin of life is an extraordinarily rare event that requires an enormous amount of random chemical exploration to find the right configuration by chance, then in the vast majority of possible universes or planets, it never happens. But by definition, we exist in a universe where it did happen, and we shouldn't be surprised to find that it happened here. Whether the observation of early life on Earth tells us anything about the frequency of life elsewhere depends on which of these interpretations is correct, and that question cannot be answered from the single data point of Earth. The hypothetical transition from chemistry to biology involved at minimum the origin of some molecule or system of molecules capable of storing information and directing its own replication. On modern Earth, this function is performed by DNA and RNA, with proteins doing most of the enzymatic work. But the chicken and egg problem of biochemistry is profound. DNA requires proteins, specifically DNA polymerases, to be copied, and proteins require DNA, through the ribosomal translation of messenger RNA, to be synthesized. How did a system emerge that requires both components to function, when neither could have existed without the other? The most widely discussed resolution is the RNA world hypothesis, which proposes that RNA, a molecule that can both store information, like DNA, and catalyze chemical reactions, like proteins, through its three-dimensional folding into ribozymes, preceded the DNA protein system and served as the original biological molecule capable of both information storage and catalysis. In this view, the first life was RNA-based, with DNA and proteins arising later as more efficient specialists. Significant experimental support for this hypothesis has accumulated. Our Na catalysts have been shown to perform a wide range of reactions relevant to early biology and under appropriate laboratory conditions. Short, our Na oligomers can spontaneously form and even undergo rudimentary template-directed copying. But the assembly of functional RNA molecules from simpler precursors under plausible early Earth conditions, without enzymes to catalyze the reactions, remains experimentally challenging, and the full pathway from simple chemistry to a self-replicating RNA system has not been demonstrated. Alternative hypotheses include the metabolism-first approach, which suggests that life began not with a self-replicating molecule, but with a set of self-sustaining metabolic reactions at mineral surfaces, hydrothermal vents, clay mineral surfaces, or iron-sulfur clusters that were gradually elaborated into the complex biochemistry of modern life. The specific environment of deep-sea hydrothermal vents, alkaline, with strong proton gradients analogous to the proton motive force that drives energy generation in modern cells, has been championed by some researchers as the likely cradle of life. The origin of life remains an active research area with genuine progress being made. New routes to the synthesis of nucleotide precursors, new understanding of how mineral surfaces might have concentrated and stabilized early biomolecules, new insights into the chemical pathways that might have led from simple organic chemistry to the complex machinery of cellular life. But a definitive, complete account of how the first life arose from non-living chemistry does not yet exist, and the consequences of this ignorance for the broader question of life's prevalence elsewhere are significant. Earth has also taught us that habitability is broader than human comfort. For a long time, life was imagined as something tied to sunlight, mild temperatures, breathable air, and stable surface conditions. That view was too narrow. Microbes live in boiling hot springs, acidic mine drainage, deep basaltic rock, hypersaline lakes, Antarctic ice, the deep ocean, and the dark chemical ecosystems around hydrothermal vents. Some organisms tolerate radiation levels that would destroy human tissue. Some survive desiccation, freezing, high pressure, or near total absence of oxygen. Life on Earth does not occupy every possible environment, but it occupies a far wider range than human intuition would have predicted. The discovery of deep-sea hydrothermal vent ecosystems in the late 20th century was especially important. These ecosystems do not depend directly on sunlight. They are powered by chemical energy from Earth's interior, reactions involving water, rock, hydrogen, sulfur compounds, and other chemical gradients. Entire communities can be built around chemosynthesis rather than photosynthesis. That matters for Europa and Enceladus because their oceans are hidden under ice, far from sunlight. If life can be powered by water-rock chemistry on Earth, then a dark ocean under an icy crust is not automatically sterile. Extremophiles also changed how scientists think about Mars. The Martian surface is harsh, cold, dry, oxidizing, irradiated, and chemically reactive. But Earth microbes show that subsurface environments can be more protected than surfaces. A world can look dead from orbit while preserving habitable niches underground. That does not mean Mars is alive. It means surface hostility is not the same as planetary impossibility. This is one of the recurring lessons of astrobiology. The first question is not whether an environment is comfortable. It is whether there is liquid or usable solvent, available energy, essential chemistry, and enough stability over time for complexity to accumulate. Within our own solar system, several worlds have been identified as candidates for harboring life, either in the present or in the past, based on the existence or suspected existence of liquid water, chemical energy sources, and conditions that wouldn't immediately be lethal to the kinds of biochemistry we understand. Mars also forces a distinction between past life and present life. A world can be habitable in its youth and sterile in its maturity. Early Mars had rivers, lakes, deltas, clay minerals, and environments where water persisted long enough to alter rock. Jezero crater, where Perseverance landed, was chosen because it once held a lake and river delta, exactly the kind of environment that on Earth can preserve evidence of microbial life. Fine-grained sedimentary rocks, clays, carbonates, sulfates, and silica-rich deposits can trap organic molecules and microscopic textures for billions of years. But modern Mars is different. Its atmosphere is thin. Liquid water is unstable at the surface under most conditions. Ultraviolet radiation reaches the ground. Cosmic rays penetrate the upper layers of soil and rock, gradually breaking down organic molecules. Perchlorates complicate chemistry. Dust storms and oxidation reshape the surface. If life exists on Mars today, the most plausible refuge is not the open surface but the subsurface. Protected rock, ice, brines, or deeper environments where radiation is reduced and water activity might occasionally be high enough for metabolism. This means Mars exploration has two related but separate goals. One is paleobiology. Did life ever exist when Mars was warmer and wetter? The other is extant life search. Does anything still survive today? Perseverance is mainly building a record of ancient environments and collecting samples. A future subsurface mission, drilling deeper than the radiation process surface, would address a different question. A negative result from one mission would not close the case. If Perseverance samples contain no life evidence, Mars could still have had life elsewhere. If surface samples are sterile, the subsurface could still matter. Mars is a planet, not a laboratory dish. The search has to be geographical, geological, and patient. Mars deserves special caution because it is the place where public excitement most easily outruns the evidence. The most important recent development is the Perseverance rover's sample from the rock, called Chiava Falls in Jezero crater. The rock contains features that NASA has described as a potential biosignature: organic carbon, chemical textures, and mineral patterns that could be consistent with reactions that, on Earth, can be associated with microbial metabolism. But the word potential is doing essential work. NASA did not announce life on Mars. It announced a sample that deserves deeper investigation because the non-biological explanations have not yet been fully ruled out. That distinction matters. A biosignature is not the same as a life detection. A potential biosignature is a feature that might have biological origin but might also be produced by abiotic chemistry. Mars is full of minerals formed in water, oxidation reduction reactions, organics delivered by meteorites, and geological processes that can mimic biology. The only responsible way to handle a claim like Chiava Falls is to say, "This is one of the most interesting samples ever collected on Mars, and it must be studied with the full power of Earth laboratories before stronger claims can be made." This is why Mars sample return has been so scientifically important and so politically difficult. Returning carefully selected Martian samples to Earth would allow researchers to use instruments far beyond what can be placed on a rover. High-resolution microscopy, isotopic measurements, organic chemistry, mineralogy, contamination control, and repeated independent analysis. But the architecture, cost, and timeline of Mars sample return have been under revision, and NASA has been reconsidering how to bring the samples back in a way that is scientifically valuable and financially achievable. Until those samples are returned, Mars remains suspended between two possibilities. It may be a world where life once arose and left faint traces in ancient lakebed rocks. Or it may be a world where chemistry came close enough to imitate life without ever becoming alive. Both outcomes are scientifically important. Only one would answer the deeper question. Mars is the most studied candidate for past habitability and perhaps for surviving refugia of life today. The evidence reviewed in the Mars episode makes clear that Mars had substantial liquid water on its surface in its early history, rivers, lakes, possibly shallow seas, and that the ancient Martian environment included the chemical conditions generally considered compatible with life. Whether life actually arose during that window of habitability is unknown. The current Martian surface is cold, dry, highly irradiated, and bathed in perchlorate chemicals toxic to many forms of life, not hospitable for surface biology. But the subsurface of Mars, shielded from radiation and potentially warmed by residual geothermal heat, might maintain liquid water and provide a habitable environment. The detection of possible methane in the Martian atmosphere, discussed in the Mars episode, remains ambiguous but could, if confirmed and shown to be biologically produced, indicate active subsurface microbiology. Europa's greatest challenge is access. The ocean may be tens of kilometers below the surface, hidden under ice that has been cracked, refrozen, irradiated, and resurfaced over time. Some regions may exchange material between ocean and surface. Others may preserve old ice no longer connected to the ocean below. Plumes, if they exist and are active at the right time, could provide direct samples, but plume activity on Europa is not as clear and persistent as on Enceladus. A spacecraft flying past Europa has to infer the ocean through gravity, magnetic fields, surface chemistry, ice-penetrating radar, thermal observations, and the geology of cracks, ridges, chaos terrain, and possible plume deposits. This indirectness makes Europa scientifically rich. Every measurement is part of a larger question. How thick is the ice shell? How salty is the ocean? How much energy moves through the system? How much exchange occurs between surface and ocean? And whether oxidants produced on the surface can reach the water below. A life-friendly Europa would need not just an ocean, but an ocean connected to chemistry. Enceladus, by contrast, has already shown exchange. Its plumes are real, persistent, and sampled. But Enceladus is small. Its ocean chemistry, longevity, and energy budget have to be understood. A small moon can be habitable if tidal heating and water-rock reactions last long enough, but the duration matters. Life needs time not only to exist, but possibly to begin. Together, Europa and Enceladus represent two different styles of ocean-world astrobiology. Europa, large and powerful, but difficult to sample. Enceladus, smaller, but actively offering material to space. If either is alive, the implications would be enormous. If both are sterile despite oceans and energy, that would also teach us something profound about the difficulty of abiogenesis. The ocean worlds are different from Mars because their possible habitats may still be active now. Europa is not interesting only because it has water. It is interesting because the water may be in contact with rock. A global ocean sealed under ice is not enough by itself. Pure water with no energy source and no chemical exchange would be a poor place for life. But if Europa's ocean interacts with a rocky seafloor, then water-rock reactions could produce chemical gradients. Tidal flexing from Jupiter's gravity supplies heat. Surface radiation from Jupiter's magnetosphere modifies Europa's ice, potentially producing oxidants that could be transported downward. If oxidants from the surface and reductants from the seafloor meet in the ocean, Europa could have chemical disequilibrium, the essential fuel for metabolism. Europa Clipper is not a life detection mission in the simple sense. It will not scoop up a fish, photograph microbes, or drill into the ocean. Its goal is to determine whether Europa has the ingredients and conditions for habitability. It will study the ice shell, ocean, geology, surface composition, and possible plumes during dozens of close flybys after reaching Jupiter. That may sound indirect, but habitability is the necessary first step. Before asking whether something lives there, we have to know what kind of environment is there. Enceladus is operationally even more tempting because it does some of the sampling for us. Its south polar plumes spray ocean material into space. Cassini detected salty ice grains, organic molecules, molecular hydrogen, and evidence consistent with hydrothermal activity. Those are not life detections, but they are exactly the kind of ingredients that make astrobiologists pay attention: water, organics, energy, and access. A dedicated Enceladus plume mission could fly through the jets with instruments designed specifically for life detection. It could search for amino acids, lipid-like molecules, cell-like structures, isotopic patterns, molecular complexity, and chemical disequilibrium. It would still need to be careful. Abiotic chemistry can be rich. But Enceladus may be one of the few places where material from a potentially habitable alien ocean is naturally delivered into space for a spacecraft to sample. Titan complicates the story because it is not simply an ocean world in the Europa-Enceladus sense. Titan has a subsurface water ocean, but its surface is dominated by liquid methane and ethane, organic haze, dunes, lakes, rivers, and a thick nitrogen atmosphere. It is too cold for Earth-like surface life using liquid water. But it is a natural laboratory for prebiotic chemistry, a world where sunlight and charged particles build complex organics in the atmosphere and rain them onto the surface. Dragonfly will not go to Titan to find a forest of methane-based organisms. It will investigate habitability, chemistry, and the pathways by which complex organic molecules evolve in an alien environment. Europa, the icy moon of Jupiter, is considered one of the most promising environments for life in the solar system, possibly second only to Earth in its potential for biological complexity. Beneath a shell of water ice, a global ocean of liquid water sits in contact with a rocky seafloor, potentially including hydrothermal vent systems driven by tidal heating from Jupiter's gravity. The ingredients for life as we understand it: liquid water, chemical energy from water-rock reactions at the seafloor, organic chemistry delivered by meteorites over geological time, appear to be present. The Europa Clipper spacecraft, launched in 2024, is currently en route to make repeated close flybys of Europa and characterize the ocean's properties through measurement of the magnetic field perturbations it induces, the thickness of the ice shell, and the composition of material ejected from the surface by impacts and from possible plumes. Enceladus, Saturn's small moon discussed in the Saturn episode, presents perhaps the most operationally direct opportunity for life detection in the solar system. Its geysers actively vent material from its subsurface ocean into space, and the Cassini spacecraft flew through these geysers multiple times, detecting water, ice, organic molecules including complex organics of biological interest, molecular hydrogen consistent with hydrothermal reactions, and silicon nanoparticles indicating hot water-rock interactions at depth. A future mission specifically designed to fly through the Enceladus plumes with sensitive biosignature detectors could, in principle, directly sample material from the ocean interior without the need to land or drill, one of the most scientifically cost-effective potential life detection opportunities in the solar system. Titan, Saturn's largest moon and the subject of the Dragonfly mission under development, presents a dramatically different type of potential habitability. At -179 degrees Celsius, water is frozen solid, but liquid methane and ethane exist at the surface, potentially serving as an alternative solvent for a profoundly different type of chemistry. Life in liquid methane would necessarily be based on radically different biochemistry than anything known on Earth, as the chemical properties of methane as a solvent differ dramatically from water. The thermodynamic availability of chemical energy in the methane-nitrogen environment of Titan's surface is very limited, and it's unclear whether sufficient energy for life is available. Nonetheless, the remarkable richness of Titan's organic chemistry, Its atmosphere synthesizes complex organic molecules in abundance from simpler precursors, makes it a fascinating laboratory for prebiotic chemistry and a scientifically worthy target regardless of whether life is present. Venus is the cautionary case for biosignatures. The phosphine debate showed how difficult this science can be. Phosphine was reported in Venus's clouds in 2020, immediately drawing attention because phosphine is difficult to explain in an oxidizing atmosphere and on Earth can be associated with biological or industrial processes. But the claim was contested almost as soon as it appeared. Other teams questioned the data processing, the spectral line identification, the possible confusion with sulfur dioxide, and the underlying chemistry. Later analyses and monitoring have kept the discussion alive rather than closing it. The correct lesson is not that Venus has life. It is also not that the phosphine question was useless. The correct lesson is that a possible biosignature is never enough by itself. A signal must be repeatable, independently confirmed, placed in atmospheric context, compared against abiotic chemistry, and measured with instruments designed for the problem. Venus is especially difficult because its clouds are chemically extreme, the atmosphere is complex, and our direct in situ measurements are limited. Future Venus missions may clarify the chemistry of the clouds, the distribution of trace gases, and the history of water loss. Whether or not Venus has any connection to biology, it is scientifically valuable because it teaches us how easily planetary environments can deceive simple interpretations. A molecule that looks interesting from far away may become less biological or more mysterious when the full planet is considered. Venus's cloud layer, at the altitude where temperature and pressure are similar to Earth's surface, has been proposed as a potential habitable environment for microbial life adapted to acidic conditions. Sulfuric acid clouds are strongly acidic, and most life on Earth would be rapidly destroyed in undiluted sulfuric acid. But some terrestrial microorganisms can tolerate acidic conditions, and the question is whether any life could be adapted to the specific extreme chemistry of Venus's clouds. The phosphine controversy discussed in the Venus episode has drawn specific attention to this possibility, though the detection itself remains scientifically contested and the abiotic explanations for any phosphine present have not been ruled out. Even the outer solar system's icy bodies, Pluto, the Kuiper Belt objects, comets, have been suggested as potential hosts for transient habitability during impacts or other heat-generating events that might briefly melt subsurface ice and create liquid water environments. These transient habitats would be short-lived by geological standards, but some researchers have argued they could be long enough for the first steps of abiogenesis. If that process is fast, a very uncertain if. There is also an ethical and scientific problem that makes the search more difficult: contamination. Earth life is extremely good at traveling with us. Spacecraft are assembled in clean rooms, sterilized, monitored, and tested, but perfect sterilization is almost impossible for complex machines. Microbes can survive dryness, cold, radiation, and long dormancy. If we send a spacecraft to a potentially habitable world and contaminate it with Earth organisms, we may damage the environment we are trying to study, and we may also confuse our own measurements. This is planetary protection. It has two directions. Forward contamination means carrying Earth life to another world. Back contamination means bringing extraterrestrial material to Earth in a way that could pose unknown risks, however unlikely. Mars sample return, Europa missions, and future Enceladus missions all have to be designed with this in mind. The scientific reason is simple. If we one day find a microbe on Mars, the first question will be whether it is Martian or something we brought. The ethical reason is larger. If another biosphere exists, even a microbial one, it would have intrinsic scientific value beyond anything else in the solar system. We should not accidentally override it before we understand it. The search for life is therefore not only about detection, it is about restraint. The more seriously we take the possibility of alien life, the more carefully we have to move. The difference between habitability and inhabitedness is one of the most important distinctions in the whole subject. A habitable environment is a place where life could, in principle, survive. An inhabited environment is a place where life actually exists. Those are not the same. A laboratory flask can contain water, nutrients, and energy and still be sterile if no organism is introduced. A planet can have oceans, chemistry, and heat and still never cross the threshold from chemistry to biology. Habitability is a necessary condition, not a guarantee. This distinction protects the science from overclaiming. Europa may be habitable. Enceladus may be habitable. Ancient Mars was habitable in many places. Some exoplanets may be in habitable zones. None of those statements says life is present. They say the environment is worth investigating. The public language around astrobiology often blurs this line because habitability is exciting. A headline says a world could support life, and the human imagination immediately fills the gap with living organisms. But the gap is the whole question. Astrobiology lives inside that gap between could and does. That is why the next decades matter so much. The field has become good at identifying potentially habitable environments. The harder stage is beginning now, distinguishing worlds that merely have ingredients from worlds where those ingredients became biology. The picture of the solar system that has emerged from planetary exploration is one of abundant water, ice on the Moon, water ice on Mars, subsurface oceans on Europa, Ganymede, Callisto, Titan, Enceladus, and possibly other icy moons, and of widespread organic chemistry. The building blocks are everywhere. Whether life has assembled those building blocks into anything organized and self-sustaining anywhere other than Earth remains to be determined. There is another possibility inside the Fermi Paradox that is less dramatic but deeply important. Civilizations may be hard to recognize because their detectable phase may be brief. Earth has been alive for billions of years, but detectable technology is extremely recent. For almost all of Earth's history, a distant observer would have seen a living planet, but not a technological one. Even after humans appeared, almost all of human history produced no radio emissions, no industrial atmospheric pollutants at modern levels, no city lights visible across interstellar distances, and no spacecraft. The technosignature window opened only very recently. It may also change quickly. If a civilization shifts from wasteful broadcasting to efficient directed communication, its leakage decreases. If it moves much of its activity underground, underwater, or into low-energy computing, its planetary signature changes. If it stabilizes ecologically, its industrial pollutants may decline. If it destroys itself, the window closes. If it becomes post-biological, its detectable signs may be entirely different from ours. This is why technological silence is hard to interpret. We are searching for behaviors based partly on one example, ourselves, during a very short transitional period. A civilization 1,000 years more advanced might not look like a louder version of 20th century Earth. It might look quieter. SETI is often imagined as a simple act of listening, but the real problem is multidimensional. A signal has a frequency, a bandwidth, a strength, a direction, a polarization, a time structure, a repetition pattern, and a duration. A civilization might transmit continuously or briefly. It might transmit toward us or in some other direction. It might use radio, optical lasers, infrared waste heat, neutrinos, or something we do not recognize as communication at all. It might not want to be detected. It might have existed 1,000,000 years ago and gone silent before humans evolved. It might arise 1,000,000 years from now. It might be close but quiet, far but loud, or common but short-lived. This is why decades of non-detection do not equal a clean answer. The search space is enormous. Radio SETI has covered important regions with increasing sophistication, but not all frequencies, not all stars, not all times, not all signal types, and not all possible forms of technology. Breakthrough Listen has dramatically expanded the scale of the search, surveying huge numbers of stars and large regions of the sky with modern instruments. But even that program samples only a fraction of the possible technosignature landscape. Technosignatures also do not have to be messages. A civilization might be detected through industrial atmospheric pollutants, city lights, artificial heat signatures, laser pulses, unusual orbital structures, radio leakage, radar beams, or large-scale engineering. Some of these ideas are speculative, but the broader point is practical. Intelligence might be easier or harder to detect depending on what it does, not just whether it exists. The silence so far, therefore, has to be interpreted with humility. We have not found another civilization. That is a fact, but we have not searched the whole galaxy in any complete sense. We have dipped instruments into a vast parameter space and found no unambiguous artificial signal yet. Radio SETI, the search for extraterrestrial intelligence using radio telescopes, has a history stretching back to 1960, when the American astronomer Frank Drake conducted Project Ozma, the first deliberate search for radio signals from other civilizations. Drake pointed the 85-foot radio telescope at Green Bank, West Virginia, at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for any anomalous signal on the 21-centimeter wavelength of neutral hydrogen emission, chosen as a cosmically obvious frequency that any technologically advanced civilization might choose for broadcasting. Project Ozma found nothing, and established a pattern that has continued ever since. Careful, thorough searches of increasing sensitivity and breadth, finding nothing conclusive. The thinking behind Radio SETI has always been straightforward. Radio waves travel at the speed of light, penetrate interstellar space with minimal absorption, and require relatively modest technology to produce and detect. A civilization capable of building a radio transmitter, technology we have had for barely over a century, could potentially signal across interstellar distances. If there are other technological civilizations in the galaxy, some of them might be broadcasting, intentionally or inadvertently, in wavelengths we could detect. The Drake equation is sometimes criticized because many of its terms are unknown. That criticism is true, but it misses the point. The equation was never a machine for producing one reliable number. It was a way to organize ignorance. Before exoplanet science, even the term for the fraction of stars with planets was uncertain. Now that term is effectively large. Planets are common. The number of potentially habitable planets is large. The astrophysical side of the equation has moved from speculation to measurement. The unknowns have shifted. The hard terms are now biological and civilizational. How often does chemistry become life? How often does life become complex? How often does complexity become intelligence? How often does intelligence build detectable technology? How long does that technology remain visible? Each term could be generous or brutally small. This is why the search for simple life and the search for intelligence are connected but not the same. A single independent microbial biosphere would strongly affect the first biological term. It would suggest life begins readily, but it would not tell us much about intelligence. A technosignature would prove technological intelligence exists elsewhere, but would not tell us how common microbes are. Different discoveries update different parts of the equation. In that sense, the Drake equation remains useful because it reminds us that the silence can have many causes. The galaxy may be quiet because life is rare, or because intelligence is rare, or because civilizations are short-lived, or because detection is hard. One silence, many possible filters. The Drake equation, formulated by Frank Drake in 1961 and used to organize a small conference that became the founding event of the modern SETI field, expresses the expected number of detectable communicating civilizations in the galaxy as a product of terms representing the rate of star formation in the galaxy, the fraction of stars with planetary systems, the average number of habitable planets per planetary system, the fraction of habitable planets that develop life, the fraction of life-bearing planets that develop intelligence, the fraction of intelligent civilizations that develop detectable technology, and the average lifetime of such civilizations during their technologically detectable phase. The Drake equation is less a predictive tool than an organizing framework. It identifies the key variables that determine how many civilizations might be out there, separating the astrophysical terms, which we now know with reasonable precision, from the biological and sociological terms, about which we know almost nothing. The astrophysical terms, star formation rate, fraction of stars with planets, habitable planets per system, have been substantially constrained by modern astronomy. The answer to the astrophysical portion of the Drake equation is large. By virtually any reasonable estimate, there are billions of potentially habitable planets in the Milky Way. It is the biological and sociological terms that remain entirely unconstrained, and the range of plausible values for these terms spans many orders of magnitude. The fraction of habitable planets that develop life could be close to 1, if life arises readily whenever conditions permit, or could be effectively 0 for all other planets if the origin of life on Earth was a unique accident requiring extraordinarily rare circumstances. The fraction of life-bearing planets that develop intelligence could be close to 1, if intelligence is a predictable evolutionary outcome, or negligibly small, if intelligence is a contingent accident of evolutionary history unlikely to be repeated. And the average lifetime of a technological civilization, the term that may be the most consequential, could be millions of years for stable, long-lived societies, or could be measured in centuries or even decades for civilizations that develop technology capable of their own destruction and fail to survive it. The product of these terms could be very large or effectively 0. Drake's own estimate at the 1961 conference was around 10 civilizations currently detectable in the galaxy. Optimistic estimates based on favorable assumptions reach millions. Pessimistic estimates, particularly those applying the rare earth arguments of Peter Ward and Donald Brownlee, which hold that complex multicellular life may require an unusually specific combination of circumstances, including long-term climate stability, plate tectonics, a large moon, a favorable impact environment shaped partly by giant planets, and a galactic location away from the most dangerous regions, suggests that intelligent life may be extraordinarily rare, perhaps even very rare on cosmic scales. The WOW signal remains valuable not because it proves anything, but because it shows what a genuinely interesting anomaly looks like. It was narrowband, which matters because natural astrophysical sources usually produce broader emission across a range of frequencies. It appeared near the hydrogen line, a frequency long discussed as potentially meaningful for interstellar communication because hydrogen is the most abundant element in the universe. It lasted as long as expected for a fixed sky source passing through the telescope beam, and it has never repeated. That last fact is decisive. Science can tolerate mystery, but confirmation requires repetition or independent supporting evidence. A one-time signal, however intriguing, cannot become a discovery. It remains a candidate, an anomaly, a reminder that the sky can produce signals we do not immediately understand. In a way, the WOW signal is a good discipline for the whole search. It invites wonder, but refuses conclusion. It says, something happened. It does not say, someone transmitted. The most famous event in the history of Radio SETI is the WOW signal, detected on August 15, 1977, by Jerry Emin working with the Big Ear Radio Telescope at Ohio State University. Emin was reviewing data printouts from the telescope survey when he noticed a sequence of alphanumeric characters representing a signal of remarkable properties. A narrowband signal at very close to the 21-centimeter hydrogen line. Lasting for the full 72 seconds, that Big Ear's beam swept across that patch of sky, with an intensity profile consistent with a point source. A signal coming from a specific direction in space rather than from a broadband, local source. Emin circled the characters and wrote, "Wow," in the margin, giving the signal its name. The WOW signal has never been detected again, despite numerous subsequent searches of the same region of sky with more sensitive instruments. Big Ear lost telescope time on the relevant region of sky on subsequent nights due to scheduling, and by the time a systematic follow-up was attempted, the signal was not present. Without a repeat detection, the signal cannot be confirmed or characterized further. Various explanations have been proposed over the decades. A signal from a natural astrophysical source of a type not identified in 1977, a signal from a human-made satellite or other terrestrial interference source that happened to arrive at the right time and frequency, or, consistent with all available evidence, but obviously far from confirmed, a genuine extraterrestrial signal that was detected once and not repeated because either the source stopped transmitting or the beam geometry didn't align again. The WOW signal occupies a strange position in SETI history. It is the most promising candidate for an extraterrestrial signal ever detected, and it is simultaneously entirely unexplained and unconfirmed. Researchers who study it carefully tend toward the conclusion that it represents the most likely genuine candidate among all SETI data collected, while acknowledging that the absence of confirmation makes any definitive claim impossible. It remains, 50 years later, what it was when Emin circled it, an intriguing, unexplained anomaly. Numerous other candidate SETI signals have been detected over the decades and subsequently explained as natural astrophysical phenomena, terrestrial interference, equipment artifacts, or simply statistical fluctuations in sensitive data. The first discovered pulsars, in 1967, were briefly considered as possible artificial signals before their physical mechanism was understood. They were even given the half-joking preliminary designation LGM-1 for Little Green Men, reflecting the thought that crossed the astronomers' minds before the natural explanation became clear. Pulsars, rapidly rotating neutron stars emitting beams of radio emission that sweep past Earth with clockwork regularity, are now used as natural precision clocks for gravitational wave detection. Their initial mystery illustrates how genuinely anomalous natural phenomena can initially suggest artificial origin before a natural explanation is found. The solar system itself is also a possible place to search for technology, though this idea must be handled carefully. If another civilization ever sent probes into our solar system, the most likely evidence might not be a radio message but an artifact, an object on the moon, in a stable orbit, on an asteroid, or somewhere in the outer solar system. The idea is speculative, but it is scientifically framed enough to be discussed under the broader category of technosignatures. The moon is especially interesting because its surface preserves records for long periods. Without weather, oceans, or plate tectonics, an artificial object could remain visible for millions of years, though micrometeorite bombardment and radiation would gradually degrade it. No evidence for such artifacts has been found. Lunar images, asteroid surveys, and planetary missions have not revealed anything artificial of extraterrestrial origin. But the search has not been exhaustive in the sense of examining every square meter at every scale. As with radio SETI, the absence of evidence is meaningful only in relation to the search actually performed. This line of thinking is useful because it broadens the question. Contact does not have to mean conversation. It could mean a probe, a relic, a beacon, a chemical signature, a megastructure, or a pattern in data. The challenge is to keep the search open without letting speculation outrun evidence. Technosignatures have their own version of the false positive problem. Human technology produces patterns nature rarely produces: narrowband radio carriers, artificial modulation, industrial pollutants, night-side illumination, waste heat, unusual orbital structures, or repeated pulses at designed intervals. But instruments are surrounded by human technology. Satellites, aircraft, ground transmitters, electronics, reflections, radar, and software artifacts can all imitate something interesting. Most candidate SETI signals are not dismissed because they are boring. They are dismissed because the Earth is radio noisy. This is why location and repetition matter. A real extraterrestrial signal should come from a fixed celestial direction, not follow a local antenna, satellite, or aircraft. It should show behavior consistent with sky motion. Ideally, it should repeat, allowing independent telescopes to confirm it. The signal should survive checks against known interference. It should be narrow, structured, or otherwise artificial in a way that natural astrophysical sources cannot easily reproduce. A single exciting candidate is not enough. The history of SETI is full of signals that looked interesting for minutes or days and then collapsed under scrutiny. That is not failure, it is filtering. The purpose of a rigorous search is not to protect exciting claims. It is to destroy weak ones until only the strong remain. If a genuine technosignature is ever found, the first days may be confusing. There will be caution, checks, re-observations, debate over interference, attempts by other observatories, and enormous public pressure. The strongest discovery will be the one that can withstand that pressure. The modern SETI landscape is more technologically sophisticated than anything available to the researchers of the 1960s through 1990s. The Breakthrough Listen initiative, funded at $100 million by Yuri Milner starting in 2015, has been conducting the most comprehensive SETI search in history, using the Green Bank Telescope, the Parkes Radio Telescope, and Meerkat and other facilities to observe millions of stars across a wide frequency range, with sensitivity dramatically better than any previous program. The amount of data generated by Breakthrough Listen is so large that it requires machine learning algorithms to process. Human examination of all the signals collected is simply not feasible with the volume now available. So far, Breakthrough Listen has not detected any signal of convincing extraterrestrial technological origin, though it has published analyses of numerous candidate signals subsequently identified as interference. Optical SETI, searching for laser pulses from other civilizations, has also been pursued with increasing seriousness over the past 2 decades, based on the recognition that a sufficiently powerful laser could be detectable across interstellar distances, and that short, powerful pulses, nanosecond flashes that would far outshine the continuous luminosity of a host star in that brief instant, might be a preferred communication method for advanced civilizations. Optical SETI surveys, while smaller in scale than radio programs, have found no convincing candidates. The SETI enterprise depends on assumptions about how other civilizations might choose to communicate that may be entirely wrong. We search at radio wavelengths because that is what we have the technology to detect, but a civilization that developed neutrino communication, quantum communication, gravitational wave communication, or some physical channel not yet known to us would be producing signals we have no means of detecting. We search for narrowband, continuous, or pulse signals because that is what we would recognize as artificial, but a sufficiently advanced civilization might communicate in broadband signals that look like noise to our detection algorithms, or might use a communication technology so efficient that no signal leaks into the surrounding environment at all. The way modern digital communications are far less radio loud than the analog broadcasts of the mid-20th century. We assume other civilizations would want to communicate or would produce detectable technological emissions, assumptions that may be wrong in either direction. There is also a scale problem in the idea of galactic silence. The Milky Way is about 100,000 light-years across. A radio message sent from one side would take 100,000 years to reach the other. A reply would take another 100,000 years. Civilizations separated by only a few thousand light-years would still face conversation delays longer than recorded human history. Even if the galaxy contains other minds, the geometry of light-speed communication makes community difficult. This does not prevent detection. A beacon could still be found. A signal could still cross space. A civilization could still leave persistent traces. But it means the galaxy is not a room where voices can easily call back and forth. It is an ocean where messages take centuries, millennia, or longer to arrive. That time delay changes the emotional meaning of SETI. We may not be looking for neighbors in the ordinary sense. We may be looking for evidence that someone, somewhere, at some other time, existed. The Fermi Paradox becomes more interesting when it is separated into timescales. The Milky Way is more than 10 billion years old. Earth has had life for perhaps more than 3.5 billion years. Complex animals have existed for only around 600 million years. Humans have existed for a few 100,000 years. Radio technology has existed for barely more than a century. A technological phase may be extremely short compared with planetary or galactic time. If civilizations are rare and short-lived, overlap becomes difficult. Two planets might both produce intelligence, but not at the same time. One civilization might transmit for 5,000 years and then go quiet, while another begins 1,000,000 years later. On galactic timescales, even thousands of years is a blink. The silence may not mean nobody ever exists. It may mean that synchronization is hard. There is also the possibility that technology becomes less visible with time. Earth was once radio loud in a crude way, with powerful analog broadcasts leaking into space. Much communication now is directed, compressed, fiber optic, satellite-based, encrypted, low power, or spread across many channels. A more advanced civilization might be even quieter, not because it is hiding, but because efficient technology leaks less energy. Or perhaps expansion is not inevitable. Human beings often imagine that any advanced civilization would colonize the galaxy because expansion is one of our historical patterns. But an alien civilization might be biological, ecological, virtual, post-biological, inward-looking, resource-efficient, risk-averse, or uninterested in physical expansion. It might explore with tiny probes or not at all. It might consider the galaxy not a frontier to occupy, but an environment to observe. The paradox remains, but each assumption inside it becomes less certain when examined closely. The Fermi Paradox, named after the physicist Enrico Fermi, who reportedly asked at a lunch in 1950, "Where is everybody?" is not actually a paradox in the logical sense. It is a tension between what seem like good reasons to expect other civilizations to be detectable and the fact that we have not detected any. Resolving this tension requires understanding either why the expectation of detection is wrong, or why the silence is not actually informative. The case for expecting to find others rests on the apparent abundance of habitable planets and the apparent ease of life's emergence on Earth. If life is common in the galaxy, some fraction of it should develop intelligence, some fraction of intelligent life should develop technology, and some fraction of technological civilizations should either transmit detectable signals or colonize the galaxy, and a galaxy-spanning civilization would presumably be detectable. The physicist Michael Hart pointed out in 1975 that even at relatively modest expansion speeds, say 10% of the speed of light, a spacefaring civilization could spread through the entire Milky Way in roughly 1,000,000 years, which is negligibly short compared to the galaxy's 10-billion-year history. If even one civilization in the galaxy's history had the ability and motivation to colonize the galaxy, they should have done so by now, and we should see evidence of them everywhere. The absence of any sign, no signals, no megastructures, no galactic-scale engineering, no evidence of ancient colonization in our solar system, is the paradox. Proposed resolutions are numerous, and they tend to cluster around three broad types. Either life or intelligence is far rarer than optimistic estimates suggest. The life is rare resolution, or technological civilizations tend to be short-lived, that they destroy themselves resolution. Or there are technological civilizations, but they are not communicating with us in detectable ways, that they're quiet resolution. The rare Earth argument is often misunderstood as a claim that planets are rare. That is no longer plausible. Planets are common. The modern rare Earth argument is subtler. Perhaps simple life is common, but complex life is rare. Earth did not go from microbes to animals quickly. For most of its history, life on Earth was microbial. The first evidence for life appears billions of years ago, but complex multicellular animals appear much later. Oxygen had to accumulate in the atmosphere and oceans. Eukaryotic cells had to evolve, perhaps through a rare symbiotic merger between microorganisms. Sexual reproduction, cellular differentiation, developmental gene networks, predation, skeletons, nervous systems, and large bodies all emerged over immense time. Intelligence capable of technology arrived extremely late, in one lineage, after many contingencies. From this perspective, the galaxy could contain many microbial worlds and very few technological ones. Europa might have microbes. Exoplanets might have bacterial mats. Mars might have once had simple life. But radio telescopes would still hear nothing, because microbes do not build transmitters. This possibility is scientifically important because it separates biological abundance from technological abundance. Finding microbial life would not solve the Fermi Paradox by itself. It would make the silence more interesting. If life is common but technology is silent, the filter must lie somewhere after life's origin, perhaps in complex cells, multicellularity, intelligence, technological longevity, or detectability. The life is rare family of resolutions includes everything from the rare Earth hypothesis, which argues that complex multicellular life requires a specific conjunction of astronomical and geological circumstances unlikely to be common, to the Great Filter hypothesis, proposed by economist Robin Hanson. The Great Filter posits that there is some step in the development from simple chemistry to galactic civilization that is extraordinarily improbable, and that this step is responsible for the apparent absence of other civilizations. If the Great Filter lies behind us, if the improbable step was the origin of life itself, or the development of eukaryotic cells, or the development of multicellular life, then we may be among a tiny minority of civilizations in the galaxy, with others simply never having made it past the filter. This interpretation would be relatively good news for humanity, implying that once a civilization gets past the filter, it has a reasonable chance of long-term survival. If the Great Filter lies ahead of us, if the improbable step is something that no technological civilization has yet managed, perhaps avoiding self-destruction through nuclear war, engineered pandemic, runaway AI, or some other existential risk, then the silence has darker implications. The very absence of other civilizations suggests that civilizations tend to fail at this future step, and we have no particular reason to expect to be exceptions. The they destroy themselves family of resolutions attributes the silence to the relatively short typical lifetime of technological civilizations. If a civilization typically remains in a radio-transmitting, space-capable phase for only a few hundred years before either destroying itself or transitioning to a mode of existence that is not externally detectable, then the number of simultaneously active and detectable civilizations in the galaxy at any given moment might be very small, even if civilizations have arisen many times over the galaxy's history. Given that the galaxy is about 10 billion years old, and we have been producing detectable radio emissions for less than a century, we would need to search a million-year window to have a reasonable chance of overlapping with another civilization's detectable phase, and that search has barely begun. Their quiet family of resolutions proposes that other civilizations exist but are not communicating in ways we can detect. The reasons might include deliberate silence. Perhaps civilizations that survive long enough realize there is danger in broadcasting, or conclude that communication with unknown others is unwise, or technological choices that make their communications invisible to us, or simply the enormous scale of the search problem. The number of stars in the Milky Way is around 200 billion, and a sustained, systematic search for radio signals from all of them at all frequencies and all times is a program that requires resources and time we have not yet committed. The analogy to searching a vast ocean for a specific fish is apt. The ocean is enormous, our net is small, and our fishing time has been very brief. The zoo hypothesis proposes that other civilizations are aware of us and have decided, individually or collectively, not to interfere with or reveal themselves to developing civilizations, similar to the way scientists might avoid disturbing an ecosystem they wish to observe naturally. The planetarium hypothesis suggests that a sufficiently advanced civilization might be capable of creating an artificial reality for us, including a constructed night sky with no signs of other intelligence. These proposals tend to be unfalsifiable and therefore scientifically unsatisfying, but they cannot be ruled out. Perhaps the most productive way to approach the Fermi Paradox is to note that it rests on assumptions that may simply be wrong in ways that aren't obvious, and that the silence is not as informative as it initially seems. The universe is about 13.8 billion years old. Complex multicellular life has existed on Earth for perhaps 600 million years. Technological civilization has existed for perhaps 10,000 years. We have been producing potentially detectable radio signals for about 100 years. We have been conducting targeted searches for extraterrestrial signals for about 60 years. The expected number of simultaneous detectable civilizations in the galaxy, even if they are common in the long run, is very sensitive to how long they remain detectable. If the typical detectable phase is a few thousand years, brief compared to the galaxy's 10 billion year history, then even if civilizations arise throughout the galaxy, the probability that any are detectable at this specific moment is low. Additionally, the search parameter space is enormous. We have searched a tiny fraction of the frequency space, a tiny fraction of the sky, over a tiny fraction of time. The SETI searches conducted so far, while impressive given their technical constraints, have been likened to searching for a particular grain of sand on one specific beach as a proxy for determining whether sand exists anywhere on Earth. The comparison is imprecise, but the point stands. Absence of detection is not equivalent to demonstrated absence, particularly when the search is as limited as SETI has necessarily been. The question also changes character significantly depending on what we're looking for. Searching for deliberate interstellar broadcasts aimed specifically at civilizations like ours assumes a motivation and communication strategy that might not exist. Searching for leaked emissions, the electromagnetic noise of an industrial civilization, analogous to Earth's own radio and television leakage, requires detecting signals far weaker than deliberate beacons, at distances where such signals are currently below our detection threshold. Searching for biosignatures in exoplanet atmospheres doesn't require any intelligence at all, just life. And this is the search that upcoming telescopes are best positioned to conduct. The most promising exoplanet targets are not necessarily the most Earth-like in the public imagination. A true Earth twin around a Sun-like star would be scientifically ideal in one sense, but observationally difficult. An Earth-sized planet transiting a Sun-like star blocks only about 1 part in 10,000 of the star's light, and its atmosphere contributes an even smaller signal. Its year-long orbit means transits happen only once per year, so collecting enough observations would take decades. Direct imaging of an Earth twin requires suppressing the star's light by roughly 10 billion times while preserving the faint reflected light of the planet nearby. For current telescopes, small planets around red dwarf stars are easier. The stars are smaller, so an Earth-sized planet blocks a larger fraction of the light. The habitable zones are closer in, so transits occur more often. The atmospheric signal is proportionally larger. That is why systems like TRAPPIST-1 receive so much attention. They are not perfect Earth analogs, but they are accessible. This creates a scientific trade-off. Red dwarf planets are easier to study, but their habitability is more complicated. Tidal locking, stellar flares, high-energy radiation, atmospheric escape, and unusual photochemistry. Sun-like star planets are more familiar but harder to measure. The first atmospheric biosignature candidate may therefore come from a planet that is not very Earth-like in its star, orbit, or climate. That will make interpretation difficult. A biosphere under a red dwarf might not look like Earth's biosphere from across light years. Its gases, clouds, surface temperature patterns, and chemistry could be different. The search for life beyond Earth is not only about finding another Earth. It is about learning how many ways a living planet can look. Beyond the solar system, the search becomes more powerful and more uncertain at the same time. A planet around another star cannot be sampled directly. For most exoplanets, we cannot see the surface. We cannot send a probe. We cannot drill, scoop, photograph cells, or return rocks. We infer. We look for the way a planet changes its star's light during a transit, or the way the planet's own thermal glow disappears during an eclipse behind the star, or the faint reflected light of the planet separated from the overwhelming glare of its sun. From those small signals, astronomers try to infer atmospheric molecules. This is where biosignatures become both exciting and dangerous. Oxygen is biologically powerful on Earth, but it can also be produced abiotically under some conditions. Methane can be biological, but it can also be geological. Carbon dioxide tells us about atmosphere and climate, not life by itself. Water vapor tells us about habitability, not biology. A single molecule is rarely enough. The most convincing biosignature would be a pattern. Gases far from chemical equilibrium, surface conditions compatible with liquid water, a stable atmosphere, and no plausible abiotic explanation. K218b illustrates the problem perfectly. JWST observations have made it one of the most important temperate sub-Neptune targets, with methane and carbon dioxide reported in major analyses and debated in others. Some studies have suggested possible features consistent with dimethyl sulfide or dimethyl disulfide, molecules that on Earth are associated with biology. But independent reanalyses find insufficient evidence for those sulfur-bearing molecules and warn that instrumental systematics, limited data, and model choices can create misleading preferences. The scientifically responsible position is clear. K218b is fascinating, but it is not evidence of alien life. This caution is not pessimism. It is how the first real biosignature detection, if it ever comes, will earn trust. The claim will have to survive hostile analysis. It will need repeated observations, multiple instruments, atmospheric modeling, stellar context, geological context, and careful treatment of false positives. The first serious candidate may not arrive as a triumphant announcement. It may arrive as a years-long argument that slowly becomes harder to explain without biology. The search for biosignatures, chemical signatures of life in exoplanet atmospheres, is the observational program most directly targeted at the question of life's prevalence beyond Earth, and it is the one most likely to yield either positive or negative results within human lifetimes. As discussed in the exoplanets episode, the techniques of transmission spectroscopy and direct imaging spectroscopy with the James Webb Space Telescope and successor observatories can, in principle, detect specific molecules in the atmospheres of transiting planets. The challenge is threefold. The signals are faint, requiring many hours to days of telescope time per target. Distinguishing biological from abiotic sources of biosignature gases requires understanding the planetary context well enough to rule out the abiotic alternatives, and the sample of planets accessible to atmospheric characterization in the near term is dominated by large planets around small, cool stars, not the Earth-Sun configuration most straightforwardly analogous to our situation. False positives are not an annoyance in biosignature science. They are the central problem. A planet can build oxygen without life if water vapor is split by ultraviolet light and hydrogen escapes to space, leaving oxygen behind. A planet around an active red dwarf can undergo atmospheric loss and chemical pathways very different from Earth's. Methane can come from biology, but also from water-rock reactions, volcanic processes, impacts, or primordial reservoirs. Sulfur gases can be biological in one context and geological in another. Even a combination of gases has to be interpreted through the planet's full environment. False negatives also matter. A living planet may not advertise itself clearly. Early Earth had life for billions of years before the atmosphere became oxygen-rich. For much of Earth's history, a distant observer might have seen methane, carbon dioxide, nitrogen, water vapor, and perhaps haze, but not a modern oxygen-rich biosignature. A world with a deep ocean and no continents might support life while producing little atmospheric signal. A planet with life under ice, like a hypothetical inhabited Europa, might be completely invisible to exoplanet spectroscopy. This means the absence of a detected biosignature is not the same as absence of life. It may mean the planet is dead. It may mean the biosphere is weak. It may mean the wrong gases are being searched. It may mean clouds hide the signal. It may mean the host star's activity complicates the spectrum. It may mean the telescope is not sensitive enough. The first generation of biosignature science will therefore be probabilistic. It will not simply label planets alive or dead. It will rank possibilities, reduce uncertainties, and build cases. That is less dramatic than fiction, but more honest. The most commonly discussed biosignature gases for an Earth-like planet are oxygen, ozone, methane, nitrous oxide, and dimethyl sulfate. Each has complications. Oxygen can be produced abiotically in specific atmospheric scenarios. Methane is produced abiotically by serpentinization of water rock systems. Nitrous oxide is present at very low concentrations in Earth's atmosphere, potentially below detection limits for current instruments at relevant distances. Dimethyl sulfate, while a promising biosignature because its abiotic production routes are less apparent, is a very minor atmospheric constituent on Earth and would be extraordinarily difficult to detect remotely. The combination of specific gases at specific concentrations is more informative than any single gas alone. The simultaneous presence of oxygen and methane in an atmosphere is particularly compelling because these two gases react with each other on timescales of decades. Any planetary atmosphere containing detectable quantities of both simultaneously must be continuously replenishing both, and the most natural explanation for such simultaneous replenishment is biological activity producing both. On Earth, biological photosynthesis produces oxygen, and microbial methanogenesis produces methane, creating exactly this disequilibrium. Webb has already demonstrated the ability to detect carbon dioxide and water vapor in exoplanet atmospheres. The sensitivity to oxygen or methane at Earth-like concentrations in a true Earth analog around a Sun-like star is, however, far beyond Webb's capability. The signal-to-noise ratio required to detect these minor atmospheric components against the backdrop of the star's light would require hundreds to thousands of transit observations. Impossible given the length of transit windows and the limited lifetime of the telescope. The Habitable Worlds Observatory concept, designed specifically for direct imaging of nearby Earth analogs around Sun-like stars rather than transit spectroscopy, would have the capability to attempt oxygen detection in the most favorable nearby cases, but is not expected to be operational until the late 2030s or 2040s if development proceeds on schedule. The TRAPPIST-1 system, with its 7 Earth-sized planets, including 3 in or near the habitable zone, within 40 light-years of Earth, represents the best near-term opportunity for biosignature searches on rocky habitable zone planets. Webb is devoting significant time to the TRAPPIST-1 planets, and results so far, suggesting no thick atmosphere on the innermost planets, are informative even as negative results, constraining what kinds of atmospheres are present and absent. The habitable zone planets, farther from the host star and requiring more observing time per transit, will take years of cumulative observation to characterize atmospheres even at the basic level of confirming whether an atmosphere is present. The context of the host star matters enormously for biosignature interpretation. The TRAPPIST-1 star is a highly active red dwarf that produces frequent ultraviolet flares. In an atmosphere illuminated by such flares, photochemistry produces molecules differently than in a Sun-like atmosphere, and the expected signatures of a biosphere would look different. Interpreting any biosignature detection requires a detailed understanding of the planet's atmospheric photochemistry in the context of its specific host star. False positives and false negatives are both real risks. This requires not just atmospheric detection, but detailed modeling of the atmospheric chemistry and, ideally, multiple complementary observations. One of the strongest reasons to keep the search calm is that the first discovery, if it comes, will probably not answer every emotional question at once. Imagine finding a convincing fossil microbe in a Martian rock. That would be historic, but it would not tell us whether Europa is alive, whether exoplanets have biospheres, or whether intelligence is common. Imagine detecting oxygen and methane on a planet 40 light-years away. That would be astonishing, but it would not tell us what organisms are there, whether they are microbial or complex, whether they have senses, or whether they know anything about the sky. Imagine receiving a narrowband radio signal. That would answer the question of technology elsewhere, but not necessarily tell us how biology began or whether life is common. Every possible answer opens another question. This is not disappointing. It is what makes the field deep. The search for life is not a door that opens into one room. It is a corridor of doors, each one leading to a more specific mystery. The most emotionally tempting version of the question is, are we alone? The most scientific version is, alone in what sense? Alone as living chemistry? Alone as complex multicellular organisms? Alone as animals with nervous systems? Alone as conscious beings? Alone as tool makers? Alone as a civilization using radio? Alone as a species asking the question? Each version has a different probability. Microbial life may be common while intelligence is rare. Intelligence may arise occasionally while technology is brief. Technology may be common but difficult to detect. Or the origin of life itself may be the rare step, making even microbes uncommon. This matters because a discovery at any level would answer only part of the question. A fossil microbe on Mars would not mean there are civilizations among the stars. A biosignature on an exoplanet would not mean intelligence. A radio signal would not tell us whether microbial life is common. Each discovery would open a new layer rather than closing the whole problem. That is why the search is plural. Rovers, orbiters, icy moon missions, telescopes, laboratory prebiotic chemistry, SETI surveys, atmospheric models, and extremophile biology are all part of the same broad question, but they attack different layers of it. The question of life in the universe does not reduce to a single answer. Instead, it should probably be thought of as a series of nested questions with different likelihoods and different observational programs. Is microbial life present on Mars, either today in the subsurface or in the geological record? This remains one of the most testable questions in astrobiology, but the timeline is no longer simple. Perseverance has collected samples that could be enormously important, yet Mars sample return has faced major cost, architecture, and schedule revisions. The question is scientifically near-term in principle, but politically and technically uncertain in practice. Are the subsurface oceans of Europa and Enceladus inhabited? Europa Clipper can tell us much more about Europa's habitability, ice shell, ocean, chemistry, and possible plumes, but it is not designed to detect life directly. A dedicated Enceladus plume sampling mission would be closer to a direct life detection opportunity, if such a mission is selected and built. Is life common on exoplanets? Biosignature searches with Webb and successor telescopes over the next few decades may detect statistical evidence for or against biospheres on a sample of habitable zone rocky planets. Does intelligent, technological life exist elsewhere in the galaxy? This remains the hardest question, with the longest search program required and the most uncertain relationship between evidence and conclusion. Each of these questions has its own timescale, its own technology requirement, and its own set of implications for understanding life's place in the universe. The silence also has different meanings at different distances. Within the solar system, silence means we have not yet found biology in places we can, at least in principle, visit. That is a concrete silence, but still incomplete, because we have barely sampled Mars, have not sampled Europa's ocean, have not returned material from Enceladus, and have not explored most subsurface environments. Around nearby stars, silence means we have not yet measured biosignatures or technosignatures with enough clarity. Across the galaxy, silence means our searches have not found an artificial signal in the limited regions of parameter space examined so far. These are not the same silence. A sterile Mars would not imply a sterile galaxy. A lack of radio signals would not imply a lack of microbes. A lack of oxygen in one exoplanet atmosphere would not imply that life is rare. The search has to keep its categories separate. This is another reason the subject needs patience. The answer may arrive locally first, or atmospherically first, or technologically first, and each route would tell a different story. The absence of definitive detection of life elsewhere should not be mistaken for evidence of absence, particularly given how early we are in the systematic search. The program of searching for life beyond Earth is roughly 60 years old for radio SETI, roughly 30 years old for serious exoplanet science, and about 20 years old for systematic astrobiology planning within the solar system. The universe is 13.8 billion years old. The disproportion between the age of the universe and the duration of our search is itself one of the most important facts to hold in mind when evaluating the significance of the current silence. Let's step back from the specific programs and observations and think about what finding life elsewhere would mean and what not finding it would mean. If life is found on Mars, ancient microbial life in the rocks of ancient lake beds, or extant life in the deep subsurface, the implications would be profound in one specific direction and ambiguous in another. They would confirm that life can arise independently on different worlds within the same solar system, making it very likely that life is widespread throughout the galaxy and universe. They would transform astrobiology from a field with one data point to one with two, allowing genuine comparative biology between two independent origins of life, profoundly illuminating what life is and how it arises. They would change how humanity sees itself, not the unique repository of biological information in a sterile universe, but one inhabited world among many. But finding Mars life would leave open the question of whether that life shares a common ancestry with Earth life. The solar system is not sterile on geological timescales. Mars and Earth exchange material continuously through meteorite impact. Rocks from Mars have landed on Earth, and rocks from Earth have presumably landed on Mars. It is genuinely possible that if life exists or existed on both planets, it arrived on one from the other via meteoritic panspermia, that Earth and Martian life are cousins rather than independent origins. Distinguishing independent origins from panspermia would require molecular biology of Martian organisms sufficient to compare their genetic code, if they have one, with Earth life, and might still be ambiguous. If life is found in the subsurface ocean of Europa or Enceladus, it would be a much stronger indication of independent origin than a discovery on Mars, because exchange of biological material between Earth and those ocean worlds is far less plausible. Even then, scientists would examine the chemistry carefully before making claims about independence. But if the biology were clearly unrelated to Earth life, the implication would be enormous. Life would have arisen at least twice in one solar system, and the galaxy would suddenly look far more biologically promising. If biosignature gases are detected in the atmosphere of a habitable zone exoplanet with appropriate statistical confidence, oxygen and methane together, in quantities requiring continuous biological replenishment, the implications would be similar and perhaps even more dramatic, because they would concern a world completely unconnected to our own solar system, an unambiguous, independent origin. If, after decades of searching, Mars sample analysis, Europa Clipper results, Webb and successor observations of nearby rocky planets, breakthrough Listens radio surveys of millions of stars, we still find nothing, that too would be informative, but interpretation would remain difficult. A non-detection can mean absence, or it can mean the wrong targets, the wrong wavelengths, the wrong biomarkers, weak instruments, rare timing, buried biospheres, or biology that does not strongly alter an atmosphere. Only a sufficiently large and sensitive survey could begin shifting the scientific consensus toward the view that life is rare. Silence is evidence only when the search is deep enough to make silence meaningful. The honest position today is that we do not know. We don't know if life exists anywhere beyond Earth. We don't know if the conditions that produced life on Earth are common or rare. We don't know if the origin of life is a likely or unlikely event. We don't know if intelligence is a common or rare outcome of evolution. And we don't know what the Fermi Paradox means, whether the silence reflects rarity of life, brevity of civilizations, or simply the limitations of our search. This uncertainty is not a failure of science. It is the genuine frontier, the actual edge of what is known. The questions are answerable in principle, at least partially, with the tools and programs currently being developed. The next few decades of astrobiology, planetary exploration, exoplanet characterization, and SETI have a reasonable chance of providing genuinely informative results on at least the first few nested questions. Whether those results tell us we are alone, or one of many, or something in between, any answer would reshape how humanity understands its place in the cosmos in ways that are difficult to fully anticipate from where we stand now. The next phase of the search will be shaped by missions that are already flying, already approved, or seriously planned. Europa Clipper is on its way to Jupiter and will transform our knowledge of Europa's habitability after arrival. Dragonfly is being built for Titan, where it will fly from place to place across an organic-rich landscape and study chemistry in a way no landed mission has ever done on an outer solar system world. Perseverance has already cached Martian samples that could become the most important astrobiological material ever returned, if a return architecture is completed. JWST is already measuring exoplanet atmospheres. Future extremely large telescopes on Earth will attempt more detailed studies of nearby rocky planets. The Habitable Worlds Observatory concept is being developed around the explicit goal of directly imaging potentially Earth-like worlds around nearby stars. This means the search is not vague. It has a pipeline: Mars samples, Europa habitability, Titan chemistry, exoplanet atmospheres, SETI surveys, technosignature searches, and laboratory origin of life experiments are all moving forward at the same time. The question may remain unanswered today, but it is being attacked from many directions. The most likely near-term outcome is not one clean answer, but a series of narrowing results. We may learn that one Mars sample is more interesting than another. We may learn Europa's ice shell is thinner or thicker than expected. We may find that TRAPPIST-1 planets lack thick atmospheres, or that one retains one. We may rule out certain biosignature interpretations. We may find no signals, but improve the limits. Each result will change the probability map. The search for life is therefore not waiting for a miracle. It is becoming an observational science. There is one final possibility that should be held carefully. The first answer may be ambiguous. Science fiction often imagines first contact as undeniable: a signal, a spacecraft, a message, a face, a voice. Real astrobiology may not unfold that way. The first sign may be a mineral texture in a Martian rock that could be biological or geological, a ratio of isotopes that leans one way but not decisively, a molecule in an exoplanet atmosphere that might be produced by life but might also come from unknown chemistry, a pattern in plume particles from Enceladus that is suggestive but not conclusive, a radio candidate that appears once and never repeats. The search for life may therefore be a long argument before it becomes an answer. That is not a weakness. It is the price of doing the question honestly. The universe is under no obligation to give us evidence in a form that satisfies human drama. If life is found, the strongest version of the discovery will be the one that survives every attempt to explain it without life. If life is not found, the strongest version of that conclusion will come only after searching enough places with enough sensitivity that absence becomes meaningful. We are not there yet. We are at the beginning of the serious search, not the end of it. There is something worth sitting with in the sheer scale of the search space, quite apart from any specific result. 2 trillion galaxies, each containing vast numbers of stars, each star potentially hosting planets. In the Milky Way alone, habitable zone rocky planets may number in the billions, and across the observable universe the number of possible worlds becomes so large that ordinary intuition fails completely. Against this backdrop, whether or not any other specific world among those countless possibilities has developed something that reproduces and metabolizes, and whether we will ever know, is a question whose answer matters in ways that go well beyond science into the deepest questions of meaning and context. We are, as far as we know, the only creatures in the universe capable of asking this question. That fact, if it is a fact, is its own kind of extraordinary, not necessarily a comfortable one. The loneliness implicit in being the only life in a universe of 2 trillion galaxies is not a small thing. But even if we are alone, the universe is not empty of significance merely because it lacks other witnesses. The light from a supernova, the structure of a galaxy, the chemistry of a nebula, These things exist and have the properties they have whether or not anyone observes them. Our presence as observers gives us the capacity to know them, to describe them, to find them beautiful or terrible or strange, which is its own kind of remarkable occurrence in a physical universe that did not require it. And if we are not alone, if, somewhere under the ice of Europa, or in the ancient rocks of Mars, or in the cloudy air of some world 40 light-years away, or somewhere in the depths of a galaxy a billion light-years distant, something lives, reproduces, and carries information from one generation to the next, then we are part of something far larger than a single planet's biological experiment. We are part of a universe in which life is woven into the structure of things, arising wherever conditions permit, exploring chemical and evolutionary possibility space across cosmic scales. Both possibilities are, in their own way, extraordinary. The search continues, patiently, carefully, with better and better tools, and an outcome is genuinely possible within human lifetimes. There is a quiet humility built into this entire field. Every method is partial. Mars rovers examine only a few square kilometers of one planet's surface. Europa Clipper will fly past Europa many times, but it will not swim in the ocean. Cassini flew through Enceladus's plumes with instruments that were not designed as modern life detection laboratories. JWST can examine some exoplanet atmospheres, but not most Earth-like planets around Sun-like stars. SETI can listen with extraordinary sensitivity in selected ways, but cannot listen to every possible signal in every possible direction at every possible time. The question is enormous and the tools are finite. That does not make the work hopeless. It makes the work cumulative. Each mission narrows ignorance. Each non-detection rules out something. Each ambiguous detection teaches us how to build a better test. Each improved telescope moves the boundary of the searchable universe outward by a little. This is how the answer will probably come, if it comes in science rather than fiction, not all at once, but by pressure. A suspicious rock, a better sample, a plume measurement, a repeated atmospheric feature, a ruled-out false positive, a signal seen again, a pattern that survives independent teams. The certainty will grow because every alternative becomes less convincing. And if the answer does not come soon, that will also become information. A quiet universe is not an empty result. It is a measurement that becomes stronger as the search becomes wider. There is also a human difficulty in this subject. We want the answer to mean something emotionally clear. If life is common, we want that to mean we are not alone. If life is rare, we want that to mean we are special. But the universe may not arrange its answers according to those emotional categories. Microbial life could be common and intelligence almost non-existent. Civilizations could exist, but be separated by time so completely that none ever meet. Life could be abundant in subsurface oceans, silent under ice, never looking at the stars. We could discover biology and still remain alone in the conversational sense. Or the reverse, we might find no life for a long time, not because life is absent, but because our instruments are still too weak. A century of searching may feel long to a civilization, but it is a very short scientific campaign against a galaxy hundreds of thousands of light-years across. The mature position is to let the question stay open without turning uncertainty into a preferred answer. Hope is not evidence. Silence is not proof. The right attitude is neither optimism nor pessimism, but disciplined attention. A final complication is that life may not announce itself at the scale we prefer. Human beings are drawn to large visible things: forests, animals, oceans, cities, signals, machines. But life on Earth began microscopically and remained microbial for most of the planet's history. If another world is alive, it may be alive in ways that are physically small and chemically subtle. A thin microbial film under ice, a slow metabolism in rock pores, a plume carrying fragments of organic material diluted into space, an atmosphere altered by organisms too small to see. A biosphere can be planetary in consequence, while microscopic in form. This is humbling because it means the first alien life may not feel alien in the dramatic way imagined by culture. It may be a pattern in mass spectra, a ratio of isotopes, a molecular distribution, a texture in ancient sediment, or a repeated atmospheric disequilibrium. The discovery might not be visually spectacular. It might be statistically and chemically overwhelming. That would still be enough. A second biology does not need to be large to change everything. It only needs to be independent. There is a quiet courage in accepting that uncertainty. It would be easier to declare the universe full of life because the idea is comforting, or to declare it empty because no signal has arrived. But neither answer is earned yet. The scientific position is harder: build better instruments, define better evidence, protect samples from contamination, question every exciting signal, and keep searching even when the result is silence. That patience is not passive. It is active discipline. It is the same discipline that turns stars into suns, nebulae into galaxies, and points of light into planets. The question of life beyond Earth may require the same long transformation from wonder to method to evidence to answer. And perhaps that is why the search matters even before it succeeds. It forces us to define life more carefully, to understand Earth more deeply, to study planets as systems, to improve telescopes, to protect other worlds, and to recognize how little one living planet can tell us about the full range of biology. The search changes science even in the absence of discovery. It makes the silence structured. It gives ignorance a map. The question remains open, but it is no longer vague. It now has targets, instruments, mission plans, statistical frameworks, and standards of evidence. That is a profound change. A civilization that once only wondered under the stars is now testing the universe for biology. That shift, from wondering to testing, is the real beginning of astrobiology. The answer has not arrived, but the question has become measurable, and that alone makes this moment in the history of science unlike any before it. And the work will continue, one sample, one spectrum, one careful non-detection, and one difficult interpretation at a time. And we leave it there, not with an answer, not yet with a second living world, but with a search that has finally become scientific, patient, careful, unfinished, and worthy of the question. Good night.